All right, in this video we get to explore single slit diffraction. So towards the end of the video we'll come back to the stop and think question. So it involves two different diffraction patterns and analyzing the differences between the two. So we'll have to hold off a little bit before we come back to that question. So first I just want to point out what it is. So if you pass light through just a single slit, so this is just one slit, this is different from what we were talking about in the previous video. So the previous videos talked about two slits and multiple slits. If you pass light through just a single slit, you still see this sort of interference pattern. But we're going to be careful and I won't use the word interference because normally that word is used for multiple different slits and the light from different slits interfering with itself. So what's going on? Why are there these dark spots, these constructive and destructive interference spots? And the answer to that is that the light is interfering with itself, which is starting to sound pretty bizarre. But you can imagine, imagine you had a wall here and you had a slit here and you had a slit here, and the rest was a wall, wall. And then you just start making more and more slits. Make a slit here, make a slit here, make a slit here, make a slit here. Pretty soon you've removed this whole thing. So you could still analyze this very similar to the way we analyzed the previous double slit and end slit setups. So in particular, light coming from right here can interfere with light coming from right here. So just because there's one slit doesn't mean that light isn't interfering with itself, right? Okay, so we want to be able to derive a formula that explains some of this phenomenon. So we won't quite touch on intensity in this video. We'll save that one for the next one. Notice how the central spot is a lot brighter than any of the other ones, and it decreases in brightness as we go out. This is already different from the two-slit interference pattern. One of the key properties we want to be able to explain by the end of this is, so see how the distance here between these dark spots is actually equally spaced? So we're seeing light projected on a screen far away. Looks like the spacing between these dark spots is equally spaced, except there's a missing dark spot right here. This is a missing dark spot. So we'll come back to this point right here, but I just wanted you to see this experimentally right here. So we'll come back, we'll derive a formula and then come back to that when we look at the formula. Right? Okay, so to derive this formula, I want to look at light that's coming from different parts of this slit. So we're going to look at, so remember, we want to look at light projected on a screen that's really, really far away. And as a result of that, the light that's coming, that's going through this slit, all the light rays are approximately parallel. So I'm going to draw a light ray here. Let's try and do it straighter than that. There we go. Light ray there. And I'm going to do one right in the center and then one that's coming just all the way, that just entered the slit over here. Okay. So by the way, your book talks about, it's not using the straight line paths, but it's talking about a different representation of waves that goes by the name Huygens principle. And it focuses on like wavelets like this. But I think it can get confusing if you stop and look at it that way. So I'm just going to continue on with the discussion the way that we talked about it last time. So your book talks about that for a little bit and then goes back to the way we normally did it. If you're wondering why, this picture on the right looks a little bit different than the one on the left. Okay, let's get back to the picture here. Let's do a different color. So let's do another pair. Let's do one right there and one right here. So this just keeps going. Let's do one more pair. Let's do maybe an orange one. Actually, I'm colorblind, so that's no good. This is better. Yeah, that should be parallel. Close enough. Whatever. So really, you can imagine you could do infinitely many such pairs. But what's true for all of these pairs is that for this blue light ray, the other one over here is half of the distance. So there's the slit width, and then half the slit width. And so I'm drawing, what I drew with the different colors here are pairs of light rays that are a distance a over 2 apart. Okay, so from here to here, this is a over 2. So let me write, this is a over 2. So I'm saying here that the slit width is a. So remember, d we used for the distance from the center of one slit to the center of the next slit for 2 slits and n slits. That we use the letter d. Here we're going to use the letter a for the width of just one slit. We're just passing through light through one slit in this video. Okay, so I'm just going to focus on the blue light right now. So the pair of blue right there. So it looks like, the way I drew it, it looks like this light ray, the one on the bottom right there, travels a little bit farther than the first one, than the one on top. So there is a path length difference between those two. Let's look at another pair though. Let's look at the 2 black lines. There was a black line right here and a black line right here, and it looks like there's also a path length difference right there. So actually for all of these pairs, and there are infinitely many such pairs that are a distance a over 2 apart, for all those pairs, they're the same path length difference. So this is one key ingredient in this proof. For all pairs, and they're all a distance a over 2 apart, the path length difference for those pairs is a over 2 sine theta. So we have in mind here that, so all of these are coming out at the same angle relative to this line right here, right, which is perpendicular to the slit. Okay, so this is just this. So the geometry here is very similar to the first video and the stuff about interference. So instead of d sine theta, here they're a distance a over 2 apart. So that's why instead of d, so normally you're used to d sine theta, right? But here it's a distance a over 2. So we can actually get dark spots. We can actually get destructive interference if, for all pairs, they cancel each other out. So if delta r is equal to, which is a over 2 sine theta, if delta r is equal to 1/2 lambda, might as well keep the plus or minus 1/2 lambda, then you get destructive interference. All right. So I'm going to take this and just multiply both sides by 2. So a sine theta equals plus or minus lambda. So a is just the slit width, lambda is the wavelength of light. This is saying that a specific angle, and there's plus or minus, there's one on both sides. This is a specific angle where you get a dark spot. Okay, so that explains one of the dark spots. How do we explain other ones? Well, you can also pair up the light so that it's not a distance a over 2 apart, but rather a over 4 apart. So I'll just write, we could have paired up light a distance a over 4 apart. So if that's the case, so if that was the case, then you'd have a light ray here and a light ray that's not right there, but actually right here. Okay, and you could have, and so you'll have a whole bunch of pairs that are just matched up right there. And so the derivation is actually really, really similar to this. So if the path length difference, so delta r is going to be a over 4 sine theta. If that's plus or minus half a wavelength, then you also get destructive interference. So same logic as before. It's just we could pair them up closer together rather than the whole a whole half slit away. We don't want to pair them up like here and here, because there's only one pair that's that distance apart. You know, no other two light rays would be that far apart. So that's why we're starting with a over 2 and getting smaller from there. So if we take this equation and multiply by 4, we get a sine theta equals plus or minus 2 lambda. And actually, as long as this denominator right here is an even number, you can pair up light no matter what. So I'm going to just replace this 4 with, so this 4 could just be any even number. So just 2 times p. This is 2p. If we multiply both sides of this equation by 2p, it looks like plus or minus p lambda. So what we get here is an equation for a whole bunch of spots that have destructive interference. So a sine theta is equal to plus or minus, and really let's allow p to be a negative number as well, equals p lambda. These are all points of destructive interference. But here p has to be a non-zero integer. So it's plus or minus 1, plus or minus 2 was fine, plus or minus 3 was fine, etc. Okay, so again, this equation is pinpointing the spots, the spots on the screen, which remember are the angles theta. For every value of p, there's a different angle theta. They're labeling the spots on the screen where you're seeing destructive interference, and p has to be not equal. P is an integer that's not equal to 0. So p equals 0 is called the missing dark spot. Missing dark spot. And this exactly explains why in this picture we have a missing dark spot right at the center right there. So that center would be p equals 0 in that formula. But in the derivation, you know, it was only p had to be a non-zero integer to get destructive interference. So we only see these dark spots away from the central maximum. So the p equals 0 is the missing dark spot, but for all of these other ones, so this is p equals 1. So I'm calling the positive side on to the right here. It doesn't really, it's sort of arbitrary here. This is p equals 1, this is p equals 2, 3, 4, 5. This would be minus 1, minus 2, minus 3, minus 4, minus 5. And this keeps going. So there's a missing dark spot right in the center. Also, this whole region, so the whole spot from minus 1 to 1 is called the central maximum. So this whole region is called the central maximum. So some problems will ask, you know, how long in meters or centimeters or whatever, how long is your central maximum? So in that case, you have to find where the p equals 1 dark spot is, where the p equals minus 1 dark spot is, and then take the difference between those two spots. So if like p equals 1 is at plus 1.3 centimeters, then the central maximum is twice that distance relative to the center, right? It's double the distance from the center to p equals 1, to where that p equals 1 dark spot is. So there's a lot of tricky factors of 2 if you forget this fact. But as long as you're aware that there's a missing dark spot in the center, then you can handle those factors of 2. Okay, so my main warning here is that this equation is like so similar to the other one, right? So if you had 2 slits, or really n slits, remember it was the same formula. We had d sine theta was m lambda. And if m was an energy, these were constructive interference. Constructive interference for m as an integer. For m equals 0, plus or minus 1, plus or minus 2, etc. For one slit, it's a very similar looking formula, right? Instead of a slit separation, it's slit width. And we still have the sine theta right here. And now your book is using the letter p for this integer. Now these, for p as an integer, are destructive interference. This can get pretty confusing, as you would imagine, right? If you don't keep these straight. This is destructive interference for P equals, now I can't include 0, right? That's the missing dark spot in the center. So this is P equals plus or minus 1, plus or minus 2, etc. This can keep going forever. So these are dark spots. These label, so each of these is an equation for theta, if you know the other quantities. These give the dark spots, and these give the bright spots. Now you can use this equation on the top here, you can also use to describe the dark spots if you plug in a half integer value of m. Here it's just the dark spots for the p's. You could think of like there being bright spots somewhere in between. You know, if these are all equally spaced, then right in between is a bright spot. So you can do that in like the small angle approximation. You could say, well, just take halfway between that distance. That looks like that's a local bright spot, but it's nowhere near as bright as the central bright spot. Okay, so yeah, like I said, in the next section, we're going to focus on the intensity profile here in a little bit more detail. But the central bright spot, the central maximum, is a lot brighter than the other pieces. It's something like 80 or 90% of the total energy is between the P equals minus 1 and P equals 1. You see, yeah, so notice how they're, right here they use the small angle approximation and just simplified this formula. This A sine theta equals P lambda. So if sine theta is y over L, you can rewrite this. Here all they did was replace sine theta with theta. And then theta you probably would replace with y over L, the same as in a previous video. Okay, let's come back to this question right here. Some of these questions don't even make sense. Explain why. So I want to mention right away which ones don't make sense. And those are E and F. Don't make sense. So E and F are saying that the difference between these two pictures is because of different p-values. No, not at all. The p-values are labeling the dark spots in a diffraction pattern. So right here, this is P equals 1. This is P equals 2. This right here is P equals 3. And it looks like they're about evenly spaced. I mean, the distance from 1 to 2 is about the same as the distance from 2 to 3. So it looks like the small angle approximation is valid here. And it looks like this is minus 1, minus 2, minus 3. So P is just helping to label spots on one picture. It's not explaining the difference between two different pictures. So E and F are definitely not a reason that the two pictures are different. They're just labeling different spots within one picture. So it just doesn't even make sense. In fact, I tried to put this question on an old exam, and some TAs said this problem doesn't even make sense. Like they just disagreed with even asking this problem, so they refused to even put E and F on there. So E and F are out. They just don't even make sense as answers. So it looks like these angles are bigger. So remember, so you have to imagine like this light is coming from some source. So there's some single slit right here. And these are angles. So this is the angle that corresponds to the P equals 1 dark spot. It looks like that angle is bigger for this picture on the bottom here than for this picture right here, right? So remember, we're labeling spots on the screen with the theta rather than the y values. Okay, so we have to think about reasons why this distance would grow. So we have to go back to our formula and think about, well, what could we do with the wavelength of light and with the slit width in order to increase the distance, or increase the theta value? Okay, so let's go back. So we want to be able to answer the original problem here. So the original problem at the beginning of the video. So we're going to hold P equals 1 constant. So in other words, we're just going to look at the first dark spot relative to the center. What changes could we make? To A or theta to increase theta? right? That's exactly what the problem is saying at the beginning. It's saying that from 1 to 2, we have spread out the diffraction pattern, right? We've increased theta. So how did we do that? Well, let's see, A sine theta is equal to, so we're going to hold p equals 1 constant, so p lambda. So one way to increase theta is we could increase lambda, or we could decrease A, the slit width. Okay, so increase lambda or decrease A, both of those things will spread out the diffraction pattern, will increase theta to the first dark spot. So increase theta looks like B would be okay. Right, lambda 2 bigger than lambda 1, that means we increase lambda going from 1 to 2. Or a decrease in A, that means A2 would have to be less than A1, so B looks okay as well. Okay, so if you switch, if you have some light, say you started with green light, if you switch to red light, that's going to spread out your diffraction pattern. Okay, that's what we mean by increasing lambda, increasing the wavelength of light, decreasing the frequency. Another thing that will do it is if you decrease your slit width. So if we make it smaller and smaller and smaller, that spreads out the diffraction pattern and makes it easier to see. And in fact, that's why a lot of times we don't see diffraction patterns. We deal with slits that are too wide, and so the diffraction pattern is too close together for us to ever see. So you would need a small aperture, is what it's called, is the slit width. So this is a pretty cool phenomenon, and there are some neat demos, applications we could do. If we were in class right now, I would measure the width of my hair actually with diffraction. So you could, if you hold up your hair and you just shine a laser on it and you turn out the lights, you can see a diffraction pattern. And if you measure from the center of the diffraction pattern to the first minimum, and you measure this, you measure the capital L, the distance from the slit to the screen, you can get that angle and then find out exactly what the aperture size was, which corresponds to the width of your hair. So I did this and I got like 100 micrometers for the width of my hair. So most people are somewhere between like 30 micrometers and 150. Most people are somewhere, 100 plus or minus 50 micrometers. Okay, so one more video in this chapter. The next one, we're going to combine the effects of interference and diffraction, and also talk about the intensity a little bit. Not quite as much detail as the book, but I want to give you a flavor of what's going on in this section. Okay.